The source of information. What do we mean by this term, source of information? This term is very common. Newspaper, TV news, lecturer, me at the moment. All these are sources of information. However, what do we mean by this term, source of information, in the context of information theory? Discrete memoryless source, DMS, is a source that generates M messages, symbols, letters, and the model is defined by the probability assignment. If so, then we may say that we have a digital, discrete, memoryless source of information. Obviously, we assume that our process is stationary, which means that probability assignment does not change when we shift in time today, tomorrow, or next year. In the late 40s of last century, Mr. Shannon, an American scientist, he proposed, taking into account the 6 axioms, he proposed the following mathematical formula that defines a measure of information, the so-called entropy of the source. Please observe that in this formula we have binary logarithm, logarithmus dualis, LD in short, and we will be using this term. So this is entropy of the discrete memoryless source, measure of unpredictability, uncertainty, information content. The first source, most common source, is binary source, characterized by one probability only, and the entropy of this source as a function of probability is shown on this slide. As we can see, the maximum one is for uniform distribution of probabilities when probability of both x1 and x2 is 0.5. Then entropy of this source is 1 bit. Obviously, for p equals 0 and 1, we have actually source of one message, and there is no unpredictability in such source. Entropy is 0. Let me generalize this property. The maximum entropy of the arbitrary source of m messages is logarithmus dualis of m. An example. A single fair coin, a single toss. We have 2 results, heads or tails. Both are same, probability of both is 0.5. Then information from this experiment that we obtain from this experiment is 1 bit. 1 bit is information obtained from this experiment. Is it match or not? Well, we have to compare this information with information obtained from other experiment of the same kind. For example, a fair die single toss, 6 equally probable results, which means that we have the entropy 258, which means that for this experiment the entropy is 2.5 times larger than entropy that we have obtained from the experiment single coin single toss. The entropy of m tosses of this die will be m times larger. Now let me consider the situation that we have 2 sources and they are correlated. What it means that if source x generates xi, then we know something already about source y, and this relationship, correlation, is described by conditional probabilities. If x, then y. Well, then we may define joint probabilities using Bayes' formula, which is below here, knowing the conditional probabilities and probabilities of individual sources. We may calculate the joint probability, and we can calculate joint entropy and conditional entropies. This is joint entropy of both correlated sources, and these are conditional probabilities, entropies of x if y, of y if x. Now we can add 3 more properties of entropy, taking into account 2 correlated sources. Obviously, a joint entropy cannot be greater than entropies of individual sources. It will be equal if these sources are independent, not correlated. Entropy of source x if y cannot be greater than entropy of X. And this formula can be given the joint entropy as a sum of entropy of individual source plus conditional entropy if this source then the other source, which is explained here graphically. This circle represents the entropy of source Y, and this in a blue background is entropy of X if Y is known. At the right side we have the opposite situation, entropy of X, and at the right side entropy of Y if X is known. These two circles are overlapping. If they are not overlapping, it means that we have independent sources. Okay, the calculations. Normally we start from probability assignment of source X and conditional probabilities between X and Y. Then we may calculate conditional entropy. Straightforward from these two, we may calculate conditional entropy, and then we can calculate easily probabilities as the output from these two sets of probabilities, and other entropies, joint entropy and entropy of source Y, for example. An example, data of industrial system, a tank. And we have two sensors. One sensor is a temperature sensor. We have three levels, low, normal and high, three messages as output of this source. The second source is pressure, and we have only low and high pressure indication. And based on experiments, we have temperature sensor probabilities, these probabilities, and also joint probabilities. If so, we can easily calculate conditional probabilities and give the probabilistic model of this relationship. This probability 1 is probability that if x2 then y sub 1. Having these joint probabilities, we may calculate all the entropies here. First of all, we have to calculate the output probabilities, and then we may calculate all the entropies. Please observe that information provided by the temperature sensor, conclusions, engineering conclusions. Information provided by the temperature sensor is 151 bit, and information provided by a pressure sensor is 2/3 of this. It's lower. However, contribution of both is significant. So as a conclusion, we may say yes, it has a sense to install both sensors, because they are giving an information that contributes to the total information, and total information is 223-bit information obtained from these two sensors. This is a graphical interpretation of this. Please observe that these two circuits are not overlapping much. If they are overlapping, then practically means that there is no sense to install the second sensor. The less is overlapping area, the better. For this exemplary problem, we have entropy of y if x is given 0.72, which is 74% of entropy of y. Entropy of x if y is given is 126, which is 83% of entropy of x. Then once again, conclusion, contribution of both sources is significant. Next screencast, source with memory.